Okay, let's find some antiderivatives. So we're thinking backwards here. At first, this is confusing because you've been doing derivatives all semester, and you know power rule and chain rule, quotient rule, you know all these rules. Now you got to think of those rules backwards. You got to think there's somebody when I took his derivative that gave me 3x squared. So the derivative of x to the n, the regular old derivative, power rule says bring that n down to ground level and then drop that exponent down by 1. That's the derivative. When we're going backwards, the antiderivative of x to the n, think of this like socks and shoes. In the morning, you put on your socks, then you put on your shoes. When you get home at night, you undo that in the opposite order. First, you take off your shoes, then you take off your socks. So I want to undo this process I just did in the opposite order. So here, I multiplied by n, then drop this down by 1. To go backwards, instead of dropping down by 1, I'm going to go up by 1. And then instead of multiplying, I'm going to divide by the new exponent. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. So this guy here we'll call capital F will be this guy's antiderivative. Now listen to my words here. Typically speaking, we're going to use capital letters for antiderivatives, lowercase letters to be that guy's then derivative. You got to keep those separate or you're going to have a bad time. The antiderivative of this guy we're going to take that exponent, raise it up by 1. So 2 plus 1 is 3, dividing by the new exponent. And then, don't forget this, every time you take an antiderivative for the rest of your life, we're going to put a plus c at the end. Let's check this. Let's see if that's right. Little f is supposed to be the derivative of capital F. Let's take this guy's derivative. Well, here those 3's would just cancel, right? We would just get x cubed plus c. Let's take his derivative and check and see if we get this again. So now we're taking derivatives now. This is what we've been doing for a while. The derivative of x cubed would be 3x squared plus the derivative of a constant is just 0. Hey, look, that's what we got. Check. Let's look at this one. I would write this as x to the negative 1 power. Or we could just think about this for a minute. Think about what function, when you take his derivative, do you get 1 over x? So we got to remember, we're not taking a derivative, we're thinking backwards. What function do we already have that when we take his derivative, we get 1 over x? That's natural log. And technically, you'll see this proven when you get to calculus 2. This is actually the natural log of the absolute value of x plus c. And anytime we're taking an antiderivative, we put a plus c on. Okay. What about this guy? The antiderivative of cosine. Whose derivative is positive cosine? That would be sine of x plus c. Don't forget the plus c. We call that the constant of integration. How do we check this? Let's take his derivative. Capital F's derivative, the derivative of regular old sine is regular old cosine. The derivative of any constant is 0. Hey, that's little f of x. It worked. What about this guy? Whose derivative is e to the x? Oh, that's just regular old e to the x. Don't forget the plus c. How do we check that? The derivative of this guy, well, derivative of e to the x is just e to the x. The derivative of c, a constant, is just 0. Oh yeah, I got back what I wanted to get. So just to reiterate, let's call him like capital G of x. That is an antiderivative of this guy. That's one of the infinite many antiderivatives of this. And so is that. And so is that. I could add any number right here and I would have a different antiderivative of e to the x. There are an infinite number of antiderivatives. Because if I take the derivative of any constant right here, I'm going to get 0. So that when we're looking for the general antiderivative, we say, oh, well, there's going to be some random constant there, and we just call that random constant c. That's called our constant of integration.